Creating live broadcast. Okay, I think we are good.
How's that? We're live?
Start streaming. It says we're live. Yeah. Okay.
Works for me.
Cool. And then do you want the microphone?
Eat the mic?
Eat the mic.
Is there a stand for me?
Yeah, you can use that stand. Okay. Yeah. Will Ryan give her a little bit?
Yeah, I'm good.
Okay.
Am I good to get started?
Yeah, I think if your crowd's ready, I'd say take it away.
Is my crowd ready?
Woo! Yeah.
Yeah, there we go. Okay, all right. That's what I thought I heard. Okay, cool. We'll go ahead and get started then. So, this first workshop here, I'm going to present on some embedded systems stuff, some best practices in particular, some musings that I've acquired from some time that I spent in the aerospace industry. My name is Ryan Draves, and a little bit about me. I'm a first-year PhD student here at CU Boulder. I'm in the aerospace department, advised by Professor Nassar Ahmed in the Autonomous Systems Division. And my background is in computer science. I went to University of Michigan for that. Did a lot of robotics as well while I was there. And then I spent 3 years in the aerospace industry at a company called Astranis. So they were a startup in the Bay Area. Well, they are still doing their thing. And they made geostationary microsatellites, so particularly communication satellites. So imagine satellite internet would be a common use case for those systems. I did a lot of things there as a software engineer. Different things like a lot of the infrastructure development for our hardware testing. A lot of components need to be integrated and brought up into the larger satellite system. I wrote a lot of the test infrastructure for that. I did, every now and then, a good amount of embedded systems development. I wrote some firmware for a few of the systems that we had, primarily on the front end of the RF systems. I think like the up converters, the down converters, things that you would put on the analog front of your communications satellite. I also did a lot of DevOps, if that means anything to anyone here. So a lot of tooling with DevOps things. And if you ask me about Bazel, I won't stop talking about it. So I do love my favorite tool. Okay, so a little bit about this presentation here. This is just going over some best practices that I acquired during my time in industry, as well as a few different design philosophies that you might encounter with embedded systems. This is particularly software-oriented in terms of how you write the firmware that goes onto these systems. I have here a small project with some of the ESP32 modules. You've all either received or will be receiving one of these modules. The demos have one plugged in for you. We'll share the resource as it goes around the table. And they also have a challenge that comes with that, as well as a few bonus challenges if you're up for the task. And a small correction to the slides. I did not write bonus slides, so there will be plenty of yapping, but no bonus slide yapping. Okay, so some initial project details. It does take a while to download and install all of these things, so if you want to get started on this in the background while I present, feel free. This will be in the corner of the following slides, so I'm going to continue and you don't have to worry about missing these. But if you go to GitHub and find my repository at my name, Robo24Workshop, and then you read the README, that'll tell you how to install things, build and flash the firmware for the system. And then if you open up the main.cc file there, you can read the comments at the top and get started on the project. It'll be outlined in more detail in that location. Okay, so let's talk a little bit about this ESP32 module. This C3 variant of it is a neat little microcontroller. If any of you hail from UC Berkeley, anyone? All right, that's all right. Their little pet project is integrated into the system here. It has a RISC-V CPU, so it uses a fancy new instruction set that does things, I'm sure. It has a nice floating point module as well. That's not something you always get with embedded systems. You don't always get access to floating point operations. Sometimes you're in integer-only land. It has integrated Wi-Fi and Bluetooth, maybe a little bit fancier than floating points. You can connect this little like $4 chip to the internet and expose your local network to the broader internet. Free hacks for like $4. Very impressive. It has built-in lithium battery management, so it's very easy to make this into a little like on-the-go project or device. You can plug in a battery and it'll help manage the charging and discharging of it for you, and you don't have to worry as much about it blowing up, which is always a good thing with lithiums. It has a whopping 400 kilobytes of SRAM and 4 megabytes of flash. You can write obscenely large programs for embedded systems compared to what perhaps older chips would allow you to do. I've worked with systems where the entire program had to fit into 100 kilobytes, and let me tell you, it's not nearly as fun when you have to take all the vowels out of all of your log messages because you need to save those like 4 extra bytes. It happens, you get there eventually when you have that limited space. You don't have to worry about this. You can I put like an entire JSON C++ library into the little demo project, and it fit just perfectly, and you don't have to worry about running out of memory. It also has a bunch of nerdy cryptography things if you want to not get hacked when you connect your little $4 device to the internet. I won't go over those, whatever. It also has direct USB support. You can see that you can plug this device in over USB directly to your computer. That's pretty nice. If you've ever worked with FTDI chips to talk from USB to UART, you might know the pain of getting those things to not be finicky on you. And it also has a very comprehensive SDK on the software side, this development kit. The development kit includes most of the standard library, so anything you're familiar with STL or just general C library things as well are all available. That's quite nice. You even get free implementations of things like dynamic memory. So if you want to use dynamic memory in this program, you can, which is nice. Sometimes you don't even have that option. You have to work with static-only memory, and that can be quite limiting. As you can see as well from the diagram, we have a bunch of I/O. Of course, the point of embedded systems is to interact with the real world and send electrical signals to some physical device. And you can see here that we have lots of options to choose from. Each of these pins can act as a GPIO. They have different functions as well for standards that I won't dig into, but we'll just be working with GPIOs here. The other thing you'll see on the little demo boards at each table here is an HCSR04 ultrasonic distance sensor. So this cheap little sensor is able to measure out distance just by, similar to bats, just measuring how long it takes time of flight for an ultrasonic sound to hit something and come back to you. And you can see electrically, it's quite simple. We have here this pulse that we'll send in on the trigger pin. So this is some timed input that we'll send from the microcontroller. And that comes to the device, which tells it to send out and trigger a chirp in the ultrasonic frequency band here, hit something, whatever it is, and then it comes back. And as it comes back, it'll clock out, some pulse here that's proportional to the distance of what it measured, right? So the longer the pulse, the farther away something must be. This is a neat little device, and in theory, you can send another trigger here as soon as the previous measurement comes back. Can anyone tell me why that might be a bad idea? Any guesses?
It can hear itself.
You can hear, explain. It always hears itself.
It could if it's listening and it's like not perfectly timed up, that chirp could just propagate to and I think that's something that could extremely close.
Yes, exactly. It can echo quite literally, and even more literally here, you will have noise in your system. Literally noise in the sense that we are emitting noise and getting back noisy noise. Yes, so if you pull too fast, say as fast as you're able to, you can still get bounces off of, let's say, if I hit something nearby, but also something farther away. That farther away bounce back might arrive by the time that I send out my next signal, and now I have a bad measurement. So the datasheet recommends this sort of minimum time in between measurements, and this is what we're working with for the project here, is this idea of this sort of rate limit in terms of how fast we can drive this device before we get bad measurements. So a little more about the project here. The repository that I'm having you all clone, it contains a naive driver to handle the logic of interacting with this device, as well as a naive request handler to handle your computer sending a request to take a measurement. It does the thing and sends the result back. That's all it does. Right now, it just receives the request, takes a measurement, sends it back. It doesn't care about timing, doesn't care about anything else. It just does the thing. So included as well in this repo is this bad client. And this bad client also does not care about timing requirements. It will drive the device as fast as it can. And the challenge here is to re-implement this request handler so on the first try when you test it, you can correctly handle any sort of bad client that comes across and deal with this timing requirement that the device has. As a bonus, I have a hardware in the loop, HIDL, also known as, test for the device. I'll show later in the slides how to run it. By default, it'll fail with the base implementation, so if you get it to pass, you've probably succeeded in the first challenge here. And then as another bonus, if you're so programmatically inclined, is to also develop a script to empirically find the fastest that you can pull it at without getting bad measurements. Okay, so I'm going to try a little live demo here, and like all live demos, they're going to fail, but we're going to enjoy whatever happens.
Can I ask a question?
Of course.
What is, so in the repository there is ESP IDF that we have to download, and there's also your repository. What's the difference between these two?
Yes, so my repository is just a simple application that deals with that board that's sitting on the table there. The ESP-IDF is the software development kit that comes with Espressif, so that contains the 1.7 gigabytes of goodness that makes it really easy for anyone's laptop to be able to talk to that device. Yep. Okay, we'll go ahead and give a little demo here and try not to spoil all the surprises. So in the repo that I have here, once you have your environment set up, you can run this shell.py that I created. And I have another one of these boards, a little hard to see, it's off the side of the podium, connected, and then the sensor's pointed to the podium, so pretty close distance is what we're expecting. You can see that the shell exposes 2 clients here, and I can go ahead and request some measurements from there. The shell does support tab completion if you feel so inclined, and we can see here that if I go ahead and request some measurements, I get a pretty consistent value. It is 51 millimeters away. We are assuming that we're at sea level with this measurement, so that might be proportionally off given our altitude, but you know, give or take, it's giving a good measurement and it's doing so consistently. It also includes a timestamp. This is just the time since the microcontroller booted, so you can see that I plugged this in like, you know, a few minutes ago. We also have this bad client here, so let's go ahead and see what happens when I take some measurements with the bad client. It might be a little hard to see. Let me see if I can zoom in. There we go. So for one thing, it gave a pretty bad answer. It gave an answer much lower than the actual distance that this big client that was just doing one at a time was giving. And for another, we can see that it was doing a sampled average of 20 measurements, and it did so pretty fast. If you play video games, you would appreciate that rate of 846. If you are used to high-frequency sampling, you'll be really sad about that number. Up to you. So we can run that a few more times as well, and we'll see that we get all over the place, right? We get anywhere from 12 to, we had one that was bumped up to 43 and whatnot. It's just not giving you a good answer. And it's running in between like 600 and 1,000 hertz, which is quite impressive and also way too fast. Obviously, we're getting a lot of noise here. And included with this client as well, we have the ability to plot some of the measurements. So we will hope this works on the first try. Perfect, it does. We can see that we can plot out, I guess that doesn't zoom, that's unfortunate. We can plot out some of these measurements, and if I zoom in on a particular slice here, we can see a lot of noise. So here we can see that we get anywhere from 63 millimeters right away, farther than what it initially measured, so probably bounced back and forth, as well as low as, where did it go down to, 6 millimeters, which is probably not even within the range of what the sensor is capable of. It's probably not even able to read out that close, but it thinks it did, just because of the noise of the system here. Very noisy, as you can see. And if we go back to our client, another thing it exposes for you is that you can send a particular rate at which you want to pull it. So let's say if we drive this at 10 hertz, it'll take much longer than what it was returning earlier to do 20 measurements. But we did get the right value, 51. And if we run it a couple more times, we'll see that 51 pops out pretty consistently. And if we plot this and go back to our browser, as you run this, if you feel so inclined to go back to your browser, it'll go to your default browser when it plots this, by the way. So just open up your default browser and it'll automatically open for you. And we can see now that we have really good values. We have a little bit of noise. We have a noise at a value of 1 millimeter, but otherwise it's reading out very consistently. Now obviously 10 hertz is pretty slow. In theory we could drive this much faster. It was running at 1,000 earlier. So part of that trick and part of what the other bonus challenge is to find how fast can we really measure this for some fixed distance that you're testing out. Okay. I have no idea how to present from current slide. We're going to skip through again. Okay, so a few tips as you work on this project. Standard out is wired directly to the console on the shell. So if you do like standard C out or printf, if you are stuck using the C language, that'll show up directly on the console as you use the shell. So feel free to do print debugging if you feel so inclined. Also, you'll find the code comments will contain useful links to references like the relevant SDK methods for the ESP32 platform, as well as some datasheet details for that ultrasonic sensor. So if you need any references on what these functions are doing, everything you need should already be there if you want to just kind of copy what's there and expand on it. But if you want to read more details, that'll be linked in the comments. All right, so on to the main course here. I have a presentation on some best practices. These are just miscellaneous topics of things that I learned from a few years in the aerospace industry. This talk is mildly C++ oriented. This should apply pretty well to whatever language you're working in, whether it's C, C++, Rust, heaven forbid, MicroPython, or something else like that. But a few things every now and then will be C++ related. Okay, so my first topic here is to sanitize your inputs. So in general with software, and definitely true with embedded systems, you should not assume well-formed inputs when something comes into your device. Whether this is from the client or from the hardware, the signals that you're reading out, it's never a good idea to just blindly assume that what you got is good and run with it, right? And the motivation behind this is that when you have an error, say some corrupted request was sent, you don't want to have a failure be propagated from one part of the system to the other. So one way that this is typically known is as defensive programming as a broader practice here. And you might ask yourself the question, like, am I assuming good values in order to operate safely? And if we look at some examples here, a common failure case might be a programmer error. Let's say the bad client that I made is sending requests too fast. User error, maybe my client is neutral, doesn't lean one way or the other in badness, but the user is still allowed to do bad things if they don't know better. That can also happen. We can also get version incompatibilities. Maybe I change the structure of what this measurement request looks like, and what used to be a valid request now serializes and decodes as a very invalid new request format, and something bad happens here. So going back to this idea of failure propagation, if we have some high-level system, think of some larger robot here, like its central compute or whatnot. If it has a bug and is sending bad requests, something maybe dangerous even to the hardware, we don't want its bug to become the embedded system's bug. We want to stop that bug where it is, and do that by sanitizing those requests that we get. So a quick example that might be applied to this sensor, right? Let's say that I did want to make it so every request takes like a sampled average of a certain number of sensors. I might naively say that this is just an integer input with a field called num samples, right? And I'll send that from the client side. But what if a user picks negative infinity samples or 0 samples? In fact, let's say that we did 0 samples, so we have some value, and then we naively on the embedded system side take the average and divide by 0. What do you think happens when you divide by 0 on this system? Any guesses?
The microcontroller goes up.
Not quite. Do you have protections against that? Anyone else know what happens when you divide by 0?
Memory gets corrupted.
Not quite. It does safely handle it. Any other guesses? Good idea. Sometimes a hard fault would be a typical response. That won't be for this system. It does have a way that it deals with it. So it won't hard faults. It's also compiled without exceptions. So related to crashing, it won't throw a C++ exception because it's not compiled with any. Does this number look familiar to anyone? Might be a little small to see, but that's 4.3 billion.
What is that, the smallest integer? Sorry, biggest integer?
Yeah, that is uint32 max. That is 2 to the 32 minus 1. So somewhere probably in the compiler for this system, it defaults to the idea that if you're not going to crash or throw an exception or any other thing that happens when you divide by 0, we should return int max. Just max out the value. If they already did something wrong, It's deterministic. It's not some undefined behavior. It will always do this, but it is probably not what you wanted it to do if you take an average like that. So that would be an example, for instance. Okay, so my next idea here, just sort of a hodgepodge, going off to a different tangent here, is that optional values are safe defaults. So a little background in terms of programming logistics here is that a default is any value that a variable takes on when it's not otherwise defined. Now defaults can mean different things in different places. One way it might be a default is like a default argument in a function. This is generally bad practice in embedded systems and most anything sensitive. A default argument will, in theory, it'll take on a good value, but the bad part of it is that the programmer might not know that it takes on a certain value. They might not know about it. An example of this might be a bug that I've seen in very much the real life here, was a file system abstraction, so some high-level file system library, and it was dealing with writing to files. And the default value was that by default, the file was written to starting at the beginning of the file. You had two different options. The default argument was whether or not to append to the file. So if you chose the append flag, you would write from the end of the file and just continue on with it, like a log string, let's say. And if you didn't specify it, it would take on the default value to start from the beginning. And one of the bugs that occurred was that neither of those defaults actually cleared the file, and that wasn't very clear. And you were allowed to call into a compile if you just said, please write this value to the file. So what was happening in this system here was that some important value related to boot up, which is an integer, it was written to the file. And at some point, that integer got very large and took on an extra byte of space. And at some point, that integer got small again and it took on one less byte of space. So without knowing, the file was written to from the beginning of memory. There was an extra byte left over from the previous write, and now you have a very raw number that was written out and left over in memory. So that's a little bit of a tangent, a little different from these other ones, but in general, it's not good practice in the sense that a programmer might not know what exactly is going on with those default arguments. Also related to defaults here is the value that something takes on when it's not initialized. So you can see here, a small code example. I have the variable x and y. Neither of them are given a value here. One of them is on the stack, just this unit 32x here, and then y is put onto the heap and then is allocated. So 0 is the typical default value for integers, false for booleans, empty string for strings. What do you think the value of these two variables are as I print them out? Any guesses? One of them. Which one? Yeah, one of them will be. Truly undefined variables would have undefined behavior and take on a random value, whatever was previously in memory. For the stack variable, that will take on the 0 value, the default, and then for our read variable here, it's whatever was previously in memory. This is effectively random garbage, right? And normally the compiler for something that's explicit wouldn't let you compile with this. I did have to turn off some flags for that, but it is still possible to somehow convince the compiler that it won't be undefined when it really is. And you can see there that there's sort of ambiguity between whether or not a value is defined or whether or not it certainly actually takes on that value. And as you imagine from like a request input into device, like a request measurement, there's ambiguity between what 0 and not there means. So an optional value, if you look at like an optional class from the standard template library or your other favorite library, would clearly define whether or not something is present or not. So an example might be that if I want to read from Flash at a certain location, and the address is not set in that request method, then it might take on the value 0 by the time it gets serialized and sent to the embedded system. And that would be ill-formed, but it probably wouldn't be too bad. But imagine if I want to write to Flash at a certain location and it takes on the value 0. Does anyone know what is typically at the 0 address in Flash? This would typically be your bootloader. This is the thing that helps your program enter into its main function and actually start. So if you wrote bad values into where the bootloader is, you will probably brick your device, and you'll have to use a debugger to go get it. It is recoverable, so long as you can attach a debugger, but it certainly won't start on its own for you to be able to flash it anymore. And this could be pretty bad. If you have a robot out in the field, for instance, you might not be able to go attach the debugger. A customer may have bought it. They might not want to give it back to you for you to fix your mistake in whatever request that you sent. If you have a satellite, for instance, that corrupts like this, it tends to be very expensive to go hook a debugger up into a satellite in space. I hear space shuttle launches are a little bit more expensive these days. You got to get it out of the museum, clean it off, refuel it. Quite expensive. So a simple example here of how you could use this, if we take our none samples thing here, we take a sampled average, we could define an optional around this uint 8 here. And you can see there's a little bit of overhead. Before we use the variable, we should check whether or not it was actually populated. But now we know for certain whether or not we really meant to request 0 samples, or whether or not we really wanted to say, I forgot to send populated fields, you should probably ignore the request. If it's not populated, ignore it. If it is populated, go ahead and use the value. Okay, so another idea to look at is request handling methodologies. So for the naive implementation that I included in the repository, we have a very simple method. We receive a request to take a measurement, and then we do the thing, and then we return the results. Nothing else goes on here, just very naive. Another methodology you might encounter is a very strict one, where we might raise, quote-unquote, an error, send some sort of error message back to the device. Maybe it raises an exception when it receives one. Or otherwise just reject any sort of bad request. Just shut it out, ignore it, don't do anything with it if it seems to be ill-formed. Another way to deal with it is the engineering approach. This is my personal favorite. You take the problem, you put it somewhere else. So in this case, you might return the most recent value. Can anyone guess why that might be a problem here if you just return the most recent value if you received your request for a measurement too fast?
Your setup changed, and so you're looking for something different.
How so?
Like you're measuring at a different place, a different distance. So
Yeah, you're returning fake data essentially, right? You know, something might have actually moved, but instead of you sending the request for the measurement, you just return the previous value. So this is maybe okay if you're running fast enough where this doesn't matter. Like your robot's moving slow, but like you're pulling the measurement fast enough that doesn't quite matter. Maybe it messes with your localization algorithm. If you did this on a more expensive system, let's say you had some multi-million-dollar sensor that went onto an exploration satellite, and then you said to the scientist, so if you do something bad with it, we're just going to return to you fake data. They might get a little bit upset at you, and rightfully so, right? So it works in some cases, but this one is probably not the best case to do this approach. And then the last one that I'll talk about here is the tri-state. And that's to take the problem, this problem of, the request might be bad because it was sent too fast or something else like that, and we turn it into a state machine. So to tri-state the problem, as it's typically called here, a simple state machine might be that a system is either on, off, or into an error state. And this is extendable beyond just a simple tri-state. You might not have an off state at all. You just have n number of states plus an error state. That's fine as well. But the key detail here is that any state can go to an error state, but an error state can only go to whatever the default off state is. And the point of this system is that it requires acknowledgement, right? Something bad has happened. I received a request too fast, or my power on sequence for the robot failed, and something just went wrong. I know it went wrong, I shut it down, I'm in an error state now, and you can't just say turn it back on. You have to say turn it off first. It's already off, that's fine, but you're acknowledging that an error occurred and that you're going to clear the error before you try to turn it back on. So you can imagine some higher level software system, say your central compute on a robot or a satellite, might be stuck in some sort of naive loop, right? I want to turn the system on. If I read that it's not on, go ahead and turn it on. If I'm failing to do a power on sequence, something might be wrong at the hardware level. This could be very bad and even damaging if you try it again, right? So the idea of going into an error state and saying you have to turn it off breaks that loop. It takes that naive loop of if it's off, turn it on, and it says I'm going to reject all these requests to turn it on until someone, probably a human, acknowledges the error. So a neat trick for this as well, by the way, is that if you use enumeration for your different states in your state machine, if you make that first value, that uninitialized default 0 value, the error state, it's a little bit safer. So if you happen to get an uninitialized or default value there, it defaults to the error state. And you have a different bug, but it's still mitigated by the error state. So application of using this, for instance, would be that if we did receive that request too fast, past the rate limit of the sensor, let's say it was a hardware risk and you could burn out the sensor. You won't if you do it, by the way. You saw it was pulling in 1,000 just fine. Then we might want to have an air state there to protect against that. There is a downside to this, of course, and that's the idea of this extra overhead. From the operator's perspective, whoever's operating the robot, the satellite, whatever, dealing with this air state is a little bit cumbersome. It adds some extra overhead. What is the air? Is it safe to reset this air? And how often do I have to keep doing this? If it's going to happen every 5 minutes, I get a little annoyed. I have to send a command every 5 minutes. I have to interrupt what I'm doing to go do the thing. If it's important, that's okay. If you just requested a sensor measurement too fast, that's maybe a little bit too much overhead for this application. Okay, going off on a little different of a tangent here. It's the idea that time is a function argument. So this one comes from a long telephone game, as far as I've heard, in terms of sage advice for programming time-sensitive logic here. I've heard that the other end of the telephone was somewhere at NASA. I just don't know exactly where it originated. But certainly gets passed around in the industry quite a bit. And frequently you'll see with embedded systems, it's this idea that you have a lot of timing requirements that you need to meet. For instance, with the distance sensor, it has to be exactly like a 10 microsecond pulse on the trigger pin before it's able to acknowledge and send out the initial echo for the distance sensor. Too long, doesn't do anything. Too short, doesn't do anything. And testing this time-dependent code can be usually quite tricky, tedious, and unreliable. You can see, for example, I have a function. It's a pretty simple function. It's going to do a thing once every second. It might get called much faster than once every second, but it will simply return if it's been faster than that, and only go and actually do the thing if it's been at least 1 second. And you can imagine that testing that function is a little bit annoying. If you want to call it in sequence, different edge cases or whatnot, you have to wait a full second before it returns, or does the thing, right? And that can be a little bit tricky, and if you have, say, I don't know, noise in terms of what your operating system is doing, your test might even fail unexpectedly and be flaky. That's quite difficult to deal with. A way to mitigate this is to avoid reading and using a timestamp in the same function. Pass it down as a function argument instead. Now, it's cumbersome to sometimes design a function to do this. I made a contrived example where it's very easy to do this, but when it does work, it's quite magical. So we can see a quick rewrite of this function where all we did was move the reading of the timestamp somewhere else. Someone else is going to call this function, will pass down exactly what the timestamp is, and the first thing we do is use it. So if we look at some theoretical test code for what this sort of function might look like, back in our original implementation, there's only so many test cases we can write before this just takes forever. Say we call it, make sure it does the thing. We wait a little less than 1 second, call it, make sure it doesn't do the thing. Now we wait a little bit more, make sure it did the thing again. We can go backwards in time because we can only sleep and go forwards here for how long we're waiting. So if you have a non-monotonic clock, that's not valid anymore. If you want to test that it does the thing after a really long time, then your test is going to be really long. However, with our rewritten function that takes in timestamp as a function argument there, we can see it's much simpler to test this. I can mock out what the timestamp is. We'll just set it to 0. 1970 is a good time anyways. And we can increment it however we please, call it again, make sure it did the thing. The function will return pretty instantly, right? We're not waiting on anything, we're not sleeping anywhere. So it's pretty easy to pick these arbitrary values. We can go and hit exactly at the moment we want it to do the thing and test that precisely without it being flaky, and go backwards in time and make sure it handles that correctly. We can jump really far into the future and make sure that that handles correctly as well. So you can see that that does simplify things on the testing side, makes it much easier to deal with this. And if you had a timing requirement that was, say, not just like 10 microseconds like the sensor needs, if it was something like 5 minutes, this is where it becomes really important. If you have this system that has this long boot-up sequence or warm-up sequence or whatnot, and you're waiting 5 minutes to test every edge case, you're not going to run that test very often. You're going to hate it and despise it. But if you rewrite the function where it can run and take this 5-minute thing and turn it into like a microsecond thing, because you just go through this quickly, you'll run that test all the time. So a few cons to this, though. You do need to be careful to actually use this timestamp shortly into the function in which you were passed it. Otherwise, if you did some sort of non-trivial amount of work before you used the timestamp, it might be out of date, right? So that's where it gets a little bit tricky to design something. I have a function that needs multiple timestamps. I need to be much more careful how I design this, or I need to find some other methodology to deal with this. So the more complicated the function, the more you want to do some work after using the timestamp or before it. A little harder to do this so easily. And then, of course, passing an extra function argument is extra overhead. No one likes extra overhead. So a quick example of how you might use that in this project. We have here the definition for the handler for the request measurement. And we can rewrite it to just take in a simple timestamp. And now we can do the logic of whether or not it's been long enough since we did our last measurement request within this function. And we don't have to read out the clock ourselves in order to do that. It makes it a little bit easier to test this. All we'd have to do is mock out the hardware interactions. And now we can test this request handler very easily. Okay, going a little bit closer to the hardware and some logistics on dealing with the values that it reads out. Another idea here is that you can still do fractional math without floats. And a neat trick here that you can do is to simply multiply and divide by really large numbers, unsimplified fractions. So on some systems, you just flat out don't get floating point support. On this ESP32, it's very nice to you. It has a floating point unit. You can use it if you would like. But on almost any system, it will always be more efficient to use integer math. It takes less clock cycles on the CPU to do integer math compared to the more complicated float operations. So it becomes very desirable if you have something time sensitive to stay in the integer realm as much as you can. So with this trick, we can see here that if we assume that we're at sea level, the calculation from the duration of that signal that we get back from the device, this echo time pulse here, to millimeters is to divide by 5.8. And we could do a float operation here and divide by 5.8, but another way you can see it's done is that we multiply by 1,000 and then divide by 5,800. And I made a small error on the next slide, just pointing out if someone sees it first. One thing that we have to be careful of, though, is that as we multiply by the larger number, we don't want to overflow, right? There is a max limit here to what our uint32 can store, so you need to be careful that the values we're going to get back won't cause that multiply by 1,000 to wrap around and turn that large value into a very small one. So in this example here, if we take a look at how long it would take for the pulse width to max out a 2 to 32 here, it's approximately 1.2 hours, which is a little bit longer than it's going to do. And if we convert that back to millimeters and see what that is, this is actually meters, that is 740 kilometers, which is a little bit more than the range limit on the sensor. It's 4 meters. So we're probably safe here in this case. We can safely multiply by 1,000 and not worry about it overflowing. So no need to deal with that. If we were concerned, though, there's a neat trick. This is where my little typo is. This parentheses should be over here, is that we can upconvert to a larger integer value before we do our operation, and then we'll be sure it doesn't overflow. So then by the time that we divide again, with a smaller value, we can convert back down to a smaller integer. So we start at a uint32 with our initial width, convert that to a 64, do our multiplication, don't overflow, divide, back to a 32. Okay, this next one is my favorite. It is, oh yeah, question?
Is there any standard practice on how many zeros to multiply by converting the fraction?
Yeah, so the more zeros you add, the more arbitrary precision you're going to get, because remember that we're doing integer math here, so we're going to chop off whatever's left on that remainder, right? So if I add a bunch more zeros, I'm going to chop off some very small decimal value. In this case, for the sensor, 1,000, I just picked arbitrarily because it made the numbers look nice. Our precision here is definitely not more than a millimeter or less than a millimeter, so we don't really care as long as we're not chopping off a full millimeter worth of precision. So we have the time in microseconds, so by the time that we convert it, 1,000, it just works out nicely. That's typically a value that you'll see, but if you need more precision, just add more zeros and make sure it doesn't overflow.
Thank you.
Yep. Okay, so back to my favorite C++ concept here. This is a real thing with a real name, the static initialization order fiasco. There's a real page under that name. I just love the names that come up with some of these things. So in C++ here, when you compile, sometimes the compile will arbitrarily pick things for you, right? Like you wrote the instructions of what you want the code to do, but there's still a lot of wiggle room in terms of how to translate those instructions into the actual binary that will go onto the microcontroller, or if it's a host application, same deal, right? And typically for embedded systems, what you're compiling for is for memory. Very typically, you're going to run out of memory, so instead of the speed of the program, you're going to say, make sure that this program fits into as small of a footprint as possible so I can upload it onto the flash. And when you do this, the compiler will say, okay, I'll do whatever it takes. And whatever it takes sometimes means taking global variables and rearranging the order at which they're initialized. So when you have global variables, they get initialized before you go and enter your int main function at the start of the program. And this random ordering can get you into a lot of trouble. In particular, with most things here, as you start up the ESP32, you need to insert some data into registers in order to configure the I/O pins, right? And this usually occurs sometime during that int main, right? In this case, it's the SDK doing stuff. So I'm quite sure it's going to wait until int main to go do this and avoid the initialization order fiasco. So if you make a global variable that tries to do something in its constructor to interact with pins, you're going to interact with those pins before they've been initialized. It's going to fail. It'll have undefined behavior. It might crash the system. It might just do nothing, more than likely. But it won't do the thing that you expect it to do, which is to, like, say, set the level of a GPIO on startup. So there's a few ways to mitigate this. The first one, which you shouldn't do, but I'm just mentioning for completion's sake, is some C++ chicanery called construct on first use. I wrote the Python equivalent here. This is a much more common pattern to see in Python than it is in C++. C++ is just gross, but my opinion. So the Python pattern, if I have some sort of like property, you'll see this on the client side for what's in that shell.py, is that I have this port property that I'm going to access somewhere else, and I have this underlying variable, like underscore port, that I don't initialize until I actually use this port property. And you'll see that in the client. And the main reason I do it is that we don't try to find the ESP32 until you use the client. In theory, your program could start. You could construct a client, and it won't search for it yet. And once you're ready to use it, you plug in the ESP32. Now you actually use the client, and it'll go do the thing and search for it, find it, and start communicating with the device. So you could use that to deal with this. Much more common, though, is to only write trivial no-pin interaction constructors in C++ here. That helps deal with this fiasco, so you don't have to worry about did the pins actually get set or whatnot. And then you might move all of that initial pin logic to some other function, call it initialize, init, or whatnot, and then at the beginning of your program, call those methods manually. Okay, another issue you might encounter here with embedded systems is measuring out your stack usage. So you only have so much stack. You have those 400 kilobytes of SRAM on the system. A lot of it needs to go to the current memory in use, right? So you have some instructions that are being run that were loaded into the RAM. You have some heap that was allocated for any dynamic memory using. There's only a very limited amount of stack that's actually available. By default, on the main thread for the ESP32, they give you 3.5 kilobytes of stack to use. And stack is anything that goes into just your local space for like a function, right? You call a function, it uses stack. You initialize a variable within that function, it uses more stack. It's very easy to run out of that if you have this program that is calling a lot of functions and initializing very large variables. So it can be useful to measure out how much is being used, because when you run out of it, generally your system is going to crash, right? And it's a little bit difficult to debug your system when it's busy crashing on loop. So typically, in FreeRTOS or similar stuff, you can measure out how much of stack you've currently used on the current thread. This is usually done by having some golden value, usually like 0xAA or 55 or whatnot, and placing that in memory, and then seeing the last location where that data is still in memory, and then that's roughly how much you've used at any given point in time, right? So if you have something that's crashing because you ran out, you can comment out enough so it doesn't crash anymore, and measure out your stack remaining and see how many bytes you have left to work with before you have to start taking all those vowels out of your what messages and all those other things to reduce your memory footprint. As we can see here, I measured out the stack usage, and it was about a little more than a kilobyte was used, and 2.2 kilobytes were left. Plenty of stack to do more complicated things with this device than just read out the sensor. It's not too bad, not optimized at all, but not too bad at all. Okay, so this last section here is on testing methodologies. So in general, when you test something, you have the unit level, similar, just like the driver or an individual function that you're testing would be a unit test. You have the larger system that you're testing, the integration level test. Then you have your full system in the loop with the hardware integration testing, right? And on the unit testing, typically with embedded systems, this can be pretty hard to do, right? You're writing code that is targeted for this microcontroller. It's not meant to run on your host machine. And it can be hard to test like that, but it can also be very easy. So in addition to things like that times the function argument to make some functions a little bit easier to run, you can also do this thing called platform-based dependency selection. So in C++, right, I have a header file that might abstract what interaction with a GPIO pin might mean. But on the compilation side, the implementation of that might defer to two different files. If I want to target my microcontroller, I might compile for the ESP32 in that implementation. But if I want to run a host unit test, I might mock it out and have some host implementation that does some mocked out version of that pin interaction. And that's part of that idea is this sort of separation of concerns, right? If I abstract what a GPIO is doing, then my driver doesn't need to know about how to use a GPIO. It just knows what methods are available to use it. So if we look at some of the driver code that's there for the naive driver that I wrote, you can see that these are calling ESP32 library-specific things. I have this GPIO set level. I have this timer get time function and whatnot. But really, this driver shouldn't know how to do these things, right? The sensor is not specific to the ESP32. You can plug it into any microcontroller, any system or whatnot. It's not tied to that. But this driver is tied to that, and you can only compile it for this system. If we abstract that, though, that's when we can have this better separation of concerns. So the next idea here is integration testing. How do I test my system end-to-end, right? So without hardware in the loop, there's two different options usually for how you do this. So one of them is, instead of just abstracting away like the GPIO interactions, how can I compile my entire firmware image onto the host? So abstracting everything it does. It takes quite a bit of effort, but once you have it, it's very nice. Typically, you would also forward your I/O interactions to some sort of alongside simulation of the hardware. So I could have the emulated hardware on one side, and then my simulated hardware or simulated firmware on the other side. And I could run some sort of client test and say, end-to-end, I'm going to send a client request to my host compiled firmware. It's going to go and pretend to interact with some piece of hardware, and I'm going to read out that hardware and make sure it did the right thing, right? Another way you might do it is to compile for the target, but then run it through an emulator. Emulators are typically expensive, unless if someone is really nice to you and gives you an open source one. And typically, they'll also do the same thing for these I/O interactions, so you can write tests and make sure that the pins toggled as were expected or whatnot. But both these methodologies will enable you to do full client and firmware integration testing. So my last thing here is the full integrated hardware testbed testing. So you can imagine if we take this little system that you have on the tables there and we plug it into some machine to run automated tests. If we have some block we put in front of it at some fixed distance, we could run an end-to-end test and make sure against the hardware, I request a measurement, is it this right value? I request a lot of measurements really fast, do they all read the right thing, right? And this works pretty well. The issue usually is making it automated. Sometimes you'll see these just run manually, where some operator has to go and hit enter to go to the next part, go set up the physical thing to test the thing and whatnot. A little bit cumbersome, but with the right build infrastructure, you can make these quite easy. One idea that I wanted to share was that these are actually cacheable, and you can say that as long as the relevant code to run the test, anything client side, anywhere firmware side, hasn't changed, then when you rerun the test, it won't actually execute it against the hardware. It'll just say I have a cache result that passed, and I can go pull that result and have that as the return for this test. And if you get it cached well enough, you can actually run this on every code change. And I have seen and encountered this before, and if you ask me about Bazel, I'll tell you all about it. But you have maybe a larger repository, this larger robotic system you're working with, satellite, whatever, and on every code change, no matter how relevant, irrelevant, what it is, you ask the system to run the test against the hardware and make sure it passes. It'll either pull a cache result, or if necessary, it'll run against the hardware. And even with 150 engineers, you can still have one little test bed that'll go and run this and keep up with everyone else and all the code changes that they're making. So a quick example of this, if you want to run this hardware test for yourself, it's the file pytest.dut. You can invoke it with the tool called pytest. And by default, with the naive implementation, it will fail. If you implement the project, hopefully that this test passes. So this is a simple test that just checks based on what the data sheet says. The data sheet says pull at like no more than 60 milliseconds between measurement requests. So this test just takes a bunch of samples and makes sure that the time that it took to do so averaged at 60 milliseconds. Very simple, but automated, and you can just plug it in, run it, and see if your code passes against that test. Okay, those little icons signal the end of my presentation here. Did anyone have any questions?
So the planner's request measurement should give us a measurement, like one single instance measurement.
Yeah. The sampling thing was used to explain some of the examples here, but the request should by default just get one measurement and return it.
Yeah, so it's probably like a personal question, like subjective, but for me when I enter the plan, the entire terminal gets stuck, like hang, so that it doesn't respond, it stops responding.
Did you flash the firmware onto the microcontroller?
What was the command?
It's in the README, idf.py flash. These are all new microcontrollers. I've not flashed them with an image yet, so you'll have to build and flash the firmware for it to run for the first time. Otherwise, it just has the default image on there. It doesn't know what a measurement request is.
Thank you.
Yep. Okay, so at this point, with the remaining time for the workshop, whatever that is, I'll walk around and see how folks are doing if you're working on the project. Feel free to ask me questions and whatnot. If you have problems with the environment setup, this is also a good time to ask me. I'll help you get your Mac or Windows machine working.
I have a question.
Yep.
So, I guess where is this used like in practice? Where did you use this thing?
Oh, the sensor?
Yeah.
So the sensor is cheap and quite simple. I would say that this is usually used maybe in like a university context for like very simple, small projects. I wouldn't know of anyone using this sensor too seriously. I mean, I've seen people try to use it for like research on how well can you measure out something that's like through water or whatnot, because it can like partially see through water and whatnot. So in that context, I've seen it. Yeah, it's not the best sensor in the world. Usually you would see something like more like laser-based, like LiDAR or whatnot, would be a more practical application. My undergraduate capstone, where I got all these devices, was to make like a maze-following robot and whatnot, and do some sort of higher-level algorithmic thing. But first I didn't know where the robot was, and if you're going through a very simple grid maze, attaching 4 of these on each side of the robot was a very easy way to do that.
Ryan, do you mind if I add one thing too?
Sure.
So Ryan taught me about this the oversampling problem that he was demoing in this workshop, and I actually had just finished reviewing a paper, and I was looking at this data that they had in one of their plots, and I was like, this sensor data is so noisy, and it was an ultrasonic sensor, and they were using this exact sensor. And then when Ryan started showing me his workshop, I realized what they were doing is they were oversampling the sensor, and they were using it as a ground truth sensor for depth mapping. And then they were testing a kind of a novel new sensor to do their comparison depth mapping. And they were oversampling the ultrasonic sensor and just giving them all this garbage data. So if I had known that earlier, I would have been able to tell them that they had to slow down their sampling rate. But this is a sensor you can use, in research too. But and Alex and I are going to talk about it in the mechatronics workshop as some trade-offs for using this sensor versus using some of the other technologies too. So thanks, Brian.